Hello, welcome. We are today talking about the second fundamental theorem. Yeah, you have to decide whether it's more fun or whether it's more mental. But anyway, it is the second fundamental theorem of calculus. And it goes like this. For a continuous function, the derivative of the integral, also known as the antiderivative, of some function is the original function itself. So think about it. The derivative of the antiderivative of a function gives us the function back. Okay, notice that the original function is in terms of t and we're evaluating in terms of x, but the basic idea, the derivative of the antiderivative is the original function itself. So the derivative and the integral undo each other. They're opposite operations like addition and subtraction, multiplication and division, those sorts of things, okay? Squaring something, taking the square root. So let us go through here and see what we can do. So the derivative from negative 2 to x of t squared minus 2t. So the derivative of the antiderivative from negative 2 to x of t squared minus 2t is like this. First, we'll just do it. The derivative, let's do the antiderivative. The antiderivative of t squared is t cubed over 3 minus the antiderivative of 2t is t squared. We're going to evaluate that at x, and we're going to evaluate that at negative 2. So at x, we get x cubed over 3 minus x squared minus the back end, negative 2 cubed over 3 minus negative 2 squared. We're going to end up taking the derivative of this whole mess, so we're going to just do that right now. The derivative is, derivative of x cubed over 3 is x squared over 3, or x squared. And the derivative of x squared is 2x. The derivative of all this in the back, the constants, it's 0. So all of this goes away, and so we're left with the derivative of the antiderivative of t squared minus 2t is x squared minus 2x. Can you see a shorter way that we could have gone from here to there? Hold that thought. Okay. So let's try this one now. Okay, this time though the upper limit is sine of x. That's going to make things a little more complicated. Remember, the square root of t is t to the 1/2. Antiderivative of t to the 1/2 is t to the 3/2 divided by 3/2, which is the same as multiplying by 2/3. Sine x and 0. So we end up with 2/3 sine of x to the 3/2 minus 2/3 of 0 to the 3/2, which is just 0. Okay, now the derivative step, that says d by dx. 3/2 times 2/3 is just that, is just 1. So we have sine x to the 1/2, and now our old friend the chain rule right over here, chain rule alert, comes in and says, oh, we got to take the derivative of sine, which we know to be cosine. Okay, and so the chain rule alert says that when you're doing the second fundamental theorem of calculus and you've got something other than just x in the upper, as your upper limit, you've got to include its derivative in your final answer. Okay, that's the chain rule thing, and technically we did include the derivative of this upper limit x in the final answer, but that's just 1. So shortcut way to do this sort of problem, I would say the derivative of the antiderivative of this is I would just say the square root of sine times the cosine. Okay, I replaced this there, and then I included the derivative of the sine of x. And we're done. It's just like that. Okay? So another form of the second fundamental theorem works this way. If f prime is a rate of change, and I take the antiderivative of this rate of change, and work that out so that if big F primed is my rate of change, capital F is my function. I do capital F of B minus capital F of A, and I get the net change, or the displacement. Okay, and I'll say this a bunch of times, 183 or someplace along those lines. If you have a rate and you need a total, you should integrate. So any kind of rate that we have, if we know how fast water's leaking out of a bathtub, if we know how fast water's filling a bathtub, if we know how fast water's draining out of a pond or being evaporated, or coffee leaking out of a cup, or if somebody's running a race, we know how fast they're going, anything like that. If we have a rate and we need a total, we can integrate that rate from the start to the finish and get a total amount of change. Okay, the IBM story goes something like this. I may or may not have been in the clean room at IBM at some point with a friend of mine who worked there, and he was showing me this, that they were working on heating a chip, basically, and they used to heat it this way, and what they were trying to do was heat it this way. And what their goal was that the area under the curve was the same. And that's a really poorly drawn curve. But their goal was to have the area under the curve be the same in each process. This process would go to a higher temperature for a shorter amount of time, still the same net displacement, same impact on the chip. It would certainly save them time in terms of chip manufacturing, which is what they would want to be able to do. So they were experimenting with that, but they were looking at the net change. So if we have a motion of a particle, okay, and we want to know its net change over the course of 1 through 5 seconds, what we would do is we have a rate, and velocity is a rate, right? That's a rate. Think about rates as we have some sort of something per time that we're looking for. If we want to know the net change, we're just going to integrate. If we have a rate, we want a total, we want to integrate. In this case, from 1 to 5, t squared minus t minus 12 dt. And honestly, we just will run to the calculator and do it. We'll put t squared, x squared minus x minus 12 into the calculator. We'll graph it just to see what it looks like. And then we always want to make sure that our upper and lower limits show up in our view screen on the x direction. And then we will go to second calc, and we'll go down to integral, and our lower limit is 1, and our upper limit is 5, and it shades it in like magic. We get negative 18.667. We go back here, we write down net displacement, negative 18.666 is fine. Okay, whatever the units are. We don't know the exact units. So that's the displacement. But what you may have noticed on this particular thing is that some of it's negative and some of it's positive. So we went backwards for a while and then started to move forward. What we might be interested in is the total distance that it travels. In this case, we will just do the absolute value of t squared minus t minus 12 dt. Okay, and we'll see what that does. And the calculator will do that for us as well. So what we've got to do is we've got to go into y equals, okay, and we've got to insert, and here's where we go to math, and we find absolute value right there, number 1. And so, mine does it differently than what yours would do, so I might have to just type this in real quick, x squared minus x minus 12. And then I would go all the way over to the end here, or to here, I guess. So quick. And start deleting. Delete. Ah! Let's see what happened. After the momentary freakout. So we get the absolute value of x squared minus x minus 12. And if I were to now graph that and go to the syntax. How's that better? Like that better? All right. So when I graph this, everything stays above the x-axis. Where this used to be underneath, that's above. So I do the second calc trick, and I go down to number 7 again, and I still do my lower limit as 1. I do my upper limit as 5. I get a number, okay, 26.333, which tells me that that's how far the particle actually traveled. This is the total distance versus the net change. Okay, so that is the story, I think. Is that the story? I believe that's part of the story, and that's some of the story. It's a little more of the story. But if you have a rate and you want a total, you should integrate. That's what the real big piece of the second fundamental theorem of calculus is, that it gives us that ability to integrate rates and get totals and take the derivatives of the antiderivatives and get the function back. That is about all I've got to say for now. Thanks for stopping in, and we'll be talking to you, I would think, real soon. Bye now.